Hello, my name is Noah Lifset, and I'm going to be telling you about one of Breakthrough Listen's data processing and analysis techniques. This technique has been used by Emilio Enriquez, as well as myself, to analyze L-band data taken by the Green Bank telescope. In the future, this technique will hopefully be used on other types of data taken by other telescopes as well for Breakthrough Listen. A quick overview to start. Breakthrough Listen really starts with raw telescope data, but that data is generally too large or too difficult to manipulate, and so it is reduced to filter bank files. These filter bank files are really where this algorithm starts. Now, this algorithm will convert filter bank files to something called H5 files, which are a slightly more usable version. And once we have H5 files, the real stuff can start. The real algorithm is sort of broken down into two steps: processing and analysis. Processing searches through each observation's file to find narrowband signals, which I call hits. It'll find any narrowband signals at all. The second step, analysis, will then search through all of these narrowband signal hits for more likely ET signals, which I call candidates. Each candidate is then looked at individually and inspected and determined to be either local interference or satellites or, hopefully one day, ET. Now, a more in-depth explanation of each of these steps. So like I said, Breakthrough Listen really starts with raw data from the telescopes, but this raw data is generally too large and too difficult to manipulate, and so it is reduced by Breakthrough Listen to filter bank files. There are three types of filter bank files. There are ones with high time resolution, high frequency resolution, and a middle ground. Each observation has one of each type. This analysis looks through the high frequency resolution data because, like I said, we're looking for narrowband or laser-like signals. And for that, we need data with a resolution of about hertz. Once we have a filter bank file, we then reduce it to something called an H5 file, which is a little more usable and a little better for this algorithm, that is. Once we have the H5 file, we can begin the processing step. This step, as well as the following one, analysis, are both part of an overall algorithm called TurboSETI. The processing step, like I said, involves searching for narrowband signals. To be a little more specific, though, it involves searching for narrowband signals above a given SNR threshold at various frequency drift rates. Now, I'll break that down a little bit. SNR stands for signal-to-noise ratio, and that means that we're looking for narrowband signals whose power relative to the noise of the observation is above a given threshold. These thresholds can range from anywhere between, 10 to maybe even 50. The frequency drift rate is caused by a relative acceleration between the transmitter and the telescope. People commonly know about Doppler frequency shifts, which is caused by a relative velocity, but if the transmitter has a relative acceleration, this Doppler shift will also change over time, and that manifests itself as a frequency drift rate. We generally believe that ET transmitters will have a relative acceleration to the Earth because it would be pretty far-fetched for any ET to know the movement of the Earth and the movement of the telescope. And so this is a commonly used technique to look for ET signals. Once these signals are found, we call them hits, and they can be numbered in the millions. Each H5 file, which corresponds to one given observation, will output a .dat file with every hit found logged inside of it. An example of a DAT file is shown below. It contains a bunch of different types of information that are important. It shows the drift rate, the SNR, the frequency, the strength of the signal, information about the specific observation, such as RA and DEC, the time it was taken. And like I said, there will be tons and tons of hits for one given observation. And all of these need to be sifted through in the following step, which is called analysis. Analysis takes in .dat files for one given observation. Now there are usually 6 observations per given star, which is part of the breakthrough listen observing technique. 3 of these observations will be on target for the star, and 3 of them will be off target for the star. Now what this allows us to do is to compare these observations of on and off and see if a signal is present in both or just the on. And this is one of the common techniques used in analysis to rule out what would be local interference. We also use other types of logic to sift through these hits and rule out things that would likely be local interference or maybe even satellites. An example of another is that we will rule out anything with a drift rate of 0, because that would mean that it has to be there has to be a relative acceleration of 0 between the telescope and the transmitter, which almost definitely means the transmitter is on Earth. Now this step will narrow down millions of hits to just a few likely ones, which I call candidates. These candidates are given in the form of tables, or .csv tables. An example is shown below. These, once again, will display very vital information, such as frequency, the specific file name, the drift rate, the time and location of that specific observation. Now, there will only be a handful of candidates generally, and so each one needs to be and can be individually inspected. So far, the candidates mostly have been satellites or local transmitters that are kind of strange enough to sneak through the algorithm. But hopefully one day we will be able to find ET with these techniques. Thank you.